This is Mrs. O'Neill for AP Chemistry, Chapter 8, Section 8, Strengths of Covalent Bonds. Your objective is to observe bond strengths and how they vary with the number of shared electrons. And we're going to use the average bond enthalpy to estimate enthalpies of reactions where thermodynamic data would not be available. So you should have watched that intro video on bond length and bond energy. Again, here are my notes, but I'm going to go through them rather quickly. This is the first person to measure bond length. Gave you a nice flow chart as he always does. Talked about when you have two atoms coming together, there's attractive forces and repulsion forces. And he also talked about Goldilocks that I'm also going to use as an analogy later. He talked about this energy and the internuclear distance. And again, I want to talk about how bond energy and bond length are used in this graph and how the graph is really going, or you're reading it, from right to left, and that's going to be really, really important. And in your notes, there's also going to be an area where you're going to draw this graph and the parts. And again, reminder that that you're reading it from right to left. So he talked about, again, energy being absorbed versus energy being released. And I'm going to remind you, or strongly suggest, go back and watch 5.2.2. Again, Chapter 5, Section 2, and there's that Part 2 video. He talked about electronegativity and how bond length and bond strength are not directly related to each other, right? It's an indirect relationship between the two. And again, he gave you another example as well. Again, he talked about bond length versus bond energy, decreasing, increasing. That means it's an indirect relationship. So to recap, again, pause and read this. Make sure you're understanding this information. So back to your packet of notes. So pause the video. Again, read as you write, and don't just read the words you're writing. Read the entire sentence and then play to hear my words. So this bond is just really a force of an attraction that's keeping those atoms together to make one unit or one molecule. So we talked about the bond energy, and again, that energy is going to be how much energy is required to break that bond. And anytime we're breaking or moving things farther away from each other, that's endothermic. Those atoms or molecules, whatever needs to break apart from each other, needs to absorb energy in order to do that. And of course, that compound that is formed is going to be formed at the lowest possible energy. So in compounds, covalent compounds where they're sharing those electrons, remember that the electrons from one atom are going to be attracted to the nucleus of another. Why? Remember, electrons are negative and that nucleus is positive because of those positive protons inside. So those electrons are repelling each other from each atom and the nuclei are repelling each other from each atom. And that's why the distance that this bond length makes has to be a perfect distance in order to have the lowest amount of energy. So again, this is the graph I was talking about. I would suggest just kind of listening to what I have to say and going through this part of the video, and then you can pause and write anything you need to on the graph, as well as rewatch the video if need to. So again, this is our graph, and what's on the graph is the amount of energy, and again, we have that 0 marking here, and that internuclear distance, again, the distance between the two nucleus of each of those atoms. So, and we're also reading this graph from right to left, That's really important. You might want to write that down. So here are those two atoms. They're coming closer together. Again, notice the amount of energy is going down, right? So that's going to be negative delta H. Again, at some point, those atoms are going to come together at a perfect distance. And at that perfect distance, that's the amount of length that's going to be perfect between the two and the amount of energy between the two. So again, we kind of go with, if the atoms are getting too close together, then the energy is not going to be good and the distance is not going to be good, right? We want the lowest amount of energy. So again, that's how we're going to measure our bond length, and that's how we're going to measure our bond energy. So again, just kind of in a little bit of motion, just to make sure you're understanding, we're going or reading the graph from right to left. This is another way of looking at it. Again, we have our atoms too far apart. They're not making a bond at all. Again, they get closer together, but at some point they get so close together at a perfect distance that they make that bond in the lowest amount of energy. And of course, part 4 here, or the fourth section, those the two nuclei would be too close together where that energy or there would be repulsion, right? There would be a repulsion force between those two nuclei. So it has to be that perfect spot. So at this point, pause the video, make sure that you draw this graph, make sure you write something along the lines that you're reading it from right to left, and you can also rewind the video to make sure you're understanding all of that information. So at this point, pause the video and make sure that you read this information. I don't make you read much, so please read this information and make sure you're understanding it. So just like Goldilocks and the three bears, she had 3 different porridges to taste. One porridge was too hot, one porridge was too cold, and one porridge was just right, just like those atoms forming that bond. Some of those atoms are going to be too far away, some of the atoms are too close together, but at some point, that's the lowest amount of energy is a perfect bond distance and the perfect amount of energy to make that bond. So again, pause and read this information. Make sure you're understanding it. So this covalent bond, again, is just that force of attraction that's going to keep a group of atoms together to make a single unit or that single molecule. So if we look, for example, of CH4, we have 4 CH bonds that need to be broken. Well, they know that if they have a mole of methane gas to dissociate it into ions, it's going to take this amount of energy. So what they say is there's an average of 415 kilojoules per mole, because they're going to take that value that they have and divide by 4. So, however, we don't know if each of those CH bonds are going to have exactly the same amount of energy, right? That's why they're calling that the average. So if we simplify this, we take away one CH bond and it gets a certain amount of energy. The second one might take a little more, the third one a little less, and maybe the fourth one really less. Again, it's going to depend on the environment as well. So again, they like to quantify everything, and at this point, we don't know exactly how much energy for each of those CH bonds, but they can know how much each of the whole molecule it takes to break that bond. And because of that, they just do that average. So again, that bond is a human invention. It's just a way of explaining this energy change. So again, that model of a bond, explains nature, explains how we can observe things, and of course, it always has limitations. So again, this is even more understanding of what this model of a bond would be. So the averages of bonds, again, more bonds, more energy, the shorter the bond length. And what do we mean by that? So here is a little chart again of different bonds, their lengths and energy. So I kind of chopped it up into like the 4 sections. So if we look at this, and I like this chart a lot, because it even shows you here's 2 C's coming together. It's a single bond, but as a double bond, those carbons are going to be closer together, and as a triple bond, even closer together. So they did the same thing in all 4 situations. But if we look at this length, we are decreasing the bond length between those carbons, but the amount of energy is actually increasing. So again, you might want to make sure you're understanding this and maybe put a little notation in your notes packet in the margins. So there's ways then, obviously, of calculating. So we want to make sure we're understanding it takes energy to break those bonds. That would be endothermic, and energy to make those bonds would be exothermic. So now we can actually calculate mathematically how much energy is going to be required for a reaction to happen. So there's 2 ways to calculate it, the way we're going to do it in our notes. And if we got a chance to do the Poggle, or we might later, in the Poggle, they actually say, well, since we know that the bonds formed, since we know that the bonds formed is exothermic, we're going to make those negative numbers and then add them up. But either way, it doesn't matter. We just know that the bonds formed would be exothermic at the long run. And a reminder of 5.2.2, again, this is just a little mnemonic. Usually when you write a capital N, you're going up. So endothermic, right, is going to be going up in that graph. And when you're writing an X, you usually write the X going down first. So that would be exothermic. Again, pause the video and read the analogy. continuing, and continuing. So now let's do some calculations. So obviously they have to give you the bonds, okay? And we want to make sure we're understanding the single bonds versus a double bond versus a triple bond. So that's going to be really important. And notice all of the energies, ladies and gentlemen, all of the energies are written in the positive sense. They're always giving you that bond energy needed to break that bond. So here's our example. So the first thing we need to do is know the structures, because once we know the structures, then we're going to know what bonds are being broken, what bonds are being formed, and then we also have to take into consideration how many of each of those bonds. So of course the coefficient is going to be really important as well. So again, I like my charts, but you can just write numbers underneath each of the molecules. It's up to you. So if I fill in this chart, the HH coming from the H2 hydrogen molecule, there's one of those, the bond enthalpy they give in the chart. So it's going to be this number times 1 gives us that same number. Same thing with the chlorine. Now with the HCl, however, there's 2 bonds because of that coefficient. So the bond enthalpy they give us in the chart is that value. And of course, we have to multiply it by 2 to get the total energy change. So now I'm going to do reactants minus products. Now I already took into consideration the coefficients, but if you didn't, that's where you would put that here. Plug and chug some of the value. Again, pause and make sure you can do this in your calculator correctly and you get that value. And because there's a negative here, it is exothermic. So can you do example 2? Again, draw the structures, make sure that you have a list of each of those bonds, take your coefficients into consideration. So again, I made my charts. So here's the charts of all of my bonds broken. Here is the chart of all of my bonds formed. We can say that bonds broken minus bonds formed. Again, and I plug and chug my numbers. I get a negative 484. And again, that negative tells me it is exothermic. So for example 3, this one's a little trickier. You got more structures or more difficult structures to deal with. So try drawing them, then click through my slides to get the structures. Then you might want to make that chart. Make sure you get all of the bonds and how many there are, how much energy. There's quite a few being broken and quite a few being formed. So that's why sometimes that chart is very helpful. So here's that structure. This structure, again, it's going to be really important to count up the single bonds versus the double bonds. A lot of times I like to, as I'm counting them, kind of either X them out or draw a line through that bond, so I make sure to count up each of those bonds and how many there are. So for CH, again, how many bonds? Take into consideration the coefficient, the bond enthalpy information they give us in the chart, and then of course multiplying everything out. Then what I would do is add that up. Now again, remember, this is all in the positive sense because these are all bonds broken. Now my bonds formed. Again, how many there are, taking the coefficient into consideration, the amount of energy they give, and then of course the total change. So again, this is also in the positive sense, right? So even though these are bonds formed, the information they give us is really bonds broken. Now we can kind of plug and chug those numbers, broken minus formed. And can you come up with an answer of negative 1030 according to sig figs? And again, this would be exothermic once more. So hopefully that makes sense. If not, again, you need to ask me questions or your fellow classmates when we do the bookwork. So this is a nice example diagram of, again, things that are happening, bonds breaking, bonds formed, and where all of that energy is coming from. So to recap, can you fill in this chart all by yourself except for the bond order? And again, chemists just like to give values to everything. So they just call sometimes a single, double, and triple bond, give it a bond order. So can you fill out this chart as much as you can? Hopefully you got that, that, and that. So again, analogy, pause and make sure you're understanding. Pause and read. Pause and read. Okay, so we'll see you in class and hopefully you have questions. And again, the easiest thing to do is make those structures and draw a line through all of those bonds to make sure that you calculate those values correctly.